Now let us consider the photochemistry. Here we are going to consider the photochemical reactions. Now in every chemical reaction, reactant must be activated to overcome the barrier between the reactant and the product. In most of the cases, reactants do not have that much sufficient energy to overcome that barrier for the formation of product. In that case, we must have to reactivate the reactor. So for that purpose, energy can be supplied in terms of thermal or photochemical, right? So here we are going to consider the photochemical reactions only. Now photochemical reactions. The photochemistry is the study of chemical reaction and the physical changes that result from the interaction between the matter and the light of suitable wavelength, specifically visible and ultraviolet rays. Now in photochemical reaction, the radiation used, the range for that radiation is always 200 nanometer to 300 nanometer. So there are few examples in the nature which shows photochemical changes, photochemical reaction. The first one is the formation of D vitamin in human body, and the second one is the photosynthesis of plant, which converts the carbon dioxide into the food, carbohydrates like that. So let us understand the basic difference between the thermal and photochemical reaction. If you look at the thermal reaction, they occurs only in presence of heat. It means we need to supply the heat energy. While in photochemical reaction, they occurs in presence of light. So thermal reactions are non-selective, while the photochemical reactions are highly selective. Now let us understand this by considering example. If you consider the this-alder reaction, in that case, it requires dienes and dienophyte. It requires dienes and dienophyte. So when we are going to consider the thermal reaction, in this case we have to heated this diene also and this dienophyte also. So such type of is not a selective type. While when we are going to consider the thermal reaction, photochemical reactions, which is represented generally by this H mu is nothing but the photon. So in this case, we are going to irradiate these molecules with the different wavelengths. This is with the wavelength that is lambda 1, and this can be with the wavelength lambda 2. So it has a selectivity. So the photochemical reactions are always occur with the selectivity. Now next point, that in case of thermal reactions, the decrease in free energy always favors. That means the delta G is always negative, while in photochemical reaction, increase in free energy favors. Delta G sometimes negative, sometimes maybe positive. As the thermal reactions are happen in the presence of heat, so the temperature plays a very significant role in the thermal reactions, while in photochemical reaction temperature has a small effect. Thermal reaction, chromophore is not required, while in photochemical reaction chromophore is essential. So chromophore means the molecule which absorbs a suitable wavelength and shows color, which shows a color. So these are the carbon-carbon multiple bonds with the carbon, with oxygen, with nitrogen, carbon-carbon triple bonds. So generally those molecules which shows multiple bonds with the carbon, so being a chromophore. So now let us understand the basic theory of photochemical reactions. When the light is incident, when this photon is incident on a molecule, now it absorbs the energy and it goes into the excited state. So that asterisk represents the excitation state, right? While absorbing this molecule goes into some electronic transitions, electronic state, electronic transitions. So now let us understand. Suppose this R molecule having electrons, both the electrons are paired. So here I am going to represent the electrons with the dotted dots. Don't bother about the spin of their electrons, it can be seen later. Now let us consider only the pair means two electrons are there. So when this molecule absorbs and light energy H mu, it goes into the excitation. That means this is ground state and this is excited state. So one of the electrons stay here and one electron goes to the excited state. So this is known as electronic transition. So this is electronic transition, in which this is having lower energy and this is having higher energy. Okay, this is also known as anti-bonding orbitals, and this is known as bonding orbitals. And that energy gap is nothing but our supplied energy. Okay, the supplied energy should be higher than this, right? This is activation energy for the molecules. Now, as earlier said, that the molecule, in case of photochemical reaction, the molecule should possess a chromophore, right? Means carbon with the carbon multiple bond, carbon with the heteroatom multiple bond. Basically, we are going to consider the oxygen. Now, in this type of molecules, each molecule possesses a bonding. So this is an anti-bonding orbitals. Okay, and there are some non-bonding orbitals are also non-bonding orbitals is not there, but electrons are there. So in case of this carbon-carbon multiple bond, the bonding orbital, here it is a pi bond is there, so the bonding orbital is always represented with the pi, and the anti-bonding orbital is always represented with the pi asterisk, like star. Star indicate it is anti-bonding. Similarly, in this case, in the second case also, the carbon-oxygen double bond is there. So double bond is there, so the bonding orbital should be pi, and the anti-bonding orbital should be the pi star, because double bond is there, right? But due to presence of heteroatoms having lone pair of electrons, these are the lone pair of electrons present in oxygen atom. So due to this lone pair of electrons, molecule possesses non-bonding electrons. So they are also taking place in the transitions. So such type of transition is always represented with the n to pi star. So where n is represent the non-bonding orbitals. So this is the non-bonding electrons. Okay, they are from the non-bonding electrons. Now in case of photochemical reaction, these two transitions are plays an very important role. Pi to pi star and n to pi star transitions. So students should remember that while studying photochemical reaction, transition pi to pi star and n to pi star transitions are important. Now let us consider the photochemical process. Basically, the photochemical reactions possesses two steps, that primary and the secondary steps. While in case of primary step, the absorption and electronic excitation takes place. As earlier said, when the molecule absorbs an energy, that h mu, it goes into the excitation. Okay, so here it is absorption is take place. The molecule, this is starting material, when absorb the light, it goes into absorption and then goes into the excitation state. While in the secondary state, that excited molecule goes into some photochemical changes and get the product to form the products, that's P. So here we are not going to discuss the detailed steps, but we can discuss in when we are going to consider the Jablonski diagram. So now let us consider what is electronic excitations. So depending upon the spin, the electronic excitations are classified into the two different types, that is the singlet and triplet. So when we are going to consider a molecule having a pair of electrons, now here we are going to represent the spin. Okay, now this upward spin becomes having plus half value, while this downward spin having minus 1/2 value. Okay, so this is the spin value for this spins. Right? Upward always represent a plus 1/2 and downward always represent a minus 1/2. Now let us consider one by one. So when we are going to consider this molecule is going to be absorbed like h mu, then it goes into the excitation state, right? and the electron should be like that. One of the electron become at this ground state, and second electron goes into the excited state with the same spin as it in ground state. This is excited state. If you look at this, one electron should be in upward direction, another in downward direction. After excitation, it shows one electron in upward direction, another in downward direction. So this kind of first excitation, while we are going to consider the second excitation here. So one of the electron will be upward direction, another electron flip its spin and becomes upward direction. So now here it is both two electrons are having same spin. So these are the unpair and these are the pair. So we can say here these are the pair electrons having different spin, and this is unpair having same spin. Because you can see here both having same spin, upward direction. Here it is one is upward and another one is downward. So now let us define the singlet state. The molecule which having all spins are pair. See here it is. These are the pin pair. This is upward, this is down, so you can consider pair electrons. So this is the singlet state. This is known as singlet state. While the molecule having unpair and having same spin, so these two electrons having same spin, so these are the triplet. So this is the basic definition. Molecules having pair, they are singlet, and molecules in which two spins are unpaired having the same spin. The condition is that in case of triplet state, that two spins are unpaired and which are having the same spin. They are having the same spin. Okay. Now here we are going to calculate the spin multiplicity. Spin multiplicity. Which can be calculated by using the formula that is 2s plus 1, where s is nothing but the addition of spin of electrons. Okay, now let us calculate for the singlet state. So here it is. When we are going to consider the singlet state, in this case the spin should be like that or it should be like that. Okay, in both the cases spins are pair. One spin is upward direction, another is downward direction. This is downward and this is upward direction. So we know that when the spin in upward direction, the value is always plus 1/2, and when the spin in downward direction, the value is always correspond to the minus 1/2. So the spin s is equal to, it is addition of plus 1/2, that is plus into minus 1/2. The value is, this get cancelled, it becomes 0. So s becomes 0. So 2s plus 1 is equal to 2 into 0 plus 1 is equal to 1, and that 1 is nothing but the singlet. Okay, so when the value of spin multiplicity is 1, it means a singlet state. Similarly in case of triplet state, so both the electrons are like that, or we can say like that. Now in this case, this is also upward direction, so it having plus 1/2. This is also upward direction, it having plus 1/2. So that s is equal to plus 1/2 plus 1/2 is equal to, that is 1. So 2s plus 1 is equal to 2 into 1 plus 1 is equal to 2 plus 1, that is equal to 3. So the value 3 corresponds to the triplet. So means whenever the value of spin multiplicity is 3, state belongs to the triplet state. So this is related with the electronic excitation depending upon the spin, whether they are pair or whether they are unpaired. The electronic excitation is classified into singlet or triplet state. Now let us understand the selection rule. As we know that the selection rule is totally depends upon the electronic excitation occur in the photochemical reactions in the molecules. So the rule says that during electronic excitation there will be no change in spin. You can see here. The rule statement is that during electronic transition there will be no change in spin. It means delta S is equal to 0. Now how it can be 0? Suppose we are going to consider a molecule having a singlet state and it goes into the another singlet state. So after absorption of energy the molecule shows a transition that is a singlet. So here it is singlet, here it is singlet, that means both having same spin according to the rule. So this transition is allowed. So this is an allowed transition because both having the same spin. If you consider a transition that is triplet to triplet, again both having same spin, same state. This is triplet, this is triplet. So the transition is allowed. Now if you consider singlet to triplet or a triplet to singlet, now in both the cases, either this case singlet become a singlet transition to triplet transitions. So in both the cases these two are not equal. Here it is singlet, here it is triplet. The spin is not same. Here it is spin multiplicity is 1, while in this case it is 3. In this case 3 and it is 1. So these are not allowed transitions. So they are forbidden. They are forbidden transitions. So but the forbidden transition does not mean that this type of transition will not occur. Under certain condition, the forbidden transition becomes allowed, but it requires a certain conditions. What are these certain conditions? The first condition is that the only one I am going to consider that the energy requirement. So that should be discussed here. So since each electronic energy levels is of different kinds of vibrational energy levels. So this is V is equal to 0, V is equal to 1, this is V is equal to 2, this is V is equal to 3. Similarly, each triplet state is also combination of, this is triplet, combination of different types of vibrational energy levels. So V0, this is V is equal to 1, V is equal to 2, V is equal to 3. So when these two types of transitions are allowed, this is singlet, this is S1, this is T1, right? So one of the energy levels from vibrational energy levels from singlet state having equal energy with any one of the vibrational energy levels of triplet. So suppose this is V0 from singlet becomes equal to the V3 of triplet state. So these states are energetic states. That means they are having equal energy. So such type of transitions are allowed. So these are allowed transitions. What I mean, when the energy of two different states, either it is singlet or triplet, having same energy level, same energy vibrational levels, in that case the transition should be allowed. Okay, so here it is, you can consider that the V is nothing but the vibrational energy level in singlet state, and that V is nothing but the vibrational energy levels in triplet state. So there is having equal energy levels. So in that case the transition will be allowed transitions.